My life has been an interesting voyage. I became an astronomer because I could not imagine living on Earth and not trying to understand how the universe works. Vera Rubin, An Interesting Voyage, Annual Review of Astronomy and Astrophysics.
Whoa.
That's just one quote. Reading a few more. By about age 12, I would prefer to stay up and watch the stars than go to sleep. I started learning. I started going to the library and reading, but it was initially just watching the stars from my bedroom that I really did. There was just nothing as interesting in my life as watching the stars every night. Vera Rubin, an interview conducted by Alan P. Lightman on April 3rd, 1989 at the Niels Bohr Library and Archives. A few more. I insisted on working on problems outside the mainstream of astronomy so that I could work on my own pace and not be pressured by bandwagons. I do not offer this as an example for you, but only to show that there can be diverse approaches to science. There must be. I hope some of you will be able to devise your own path through the complex sociology of science. Science is competitive, aggressive, demanding. It is also imaginative, inspiring, uplifting. You can do it too. Vera Rubin in Where in the World is Berkeley? Graduation Address to University of California, Berkeley class of 1996, published in the book Bright Galaxies, Dark Matters, page 219. All right, I'll just read like three more. Okay. The most important feature of any telescope is the imagination with which it is used. Vera Rubin in The Dedication of the Vatican Telescope, 1993 address, published in Bright Galaxies, Dark Matter, page 80.
Let's do it.
The conclusion is inescapable that non-luminous matter exists beyond the optical galaxy. Vera Rubin in the Astrophysics Journal article, Rotational Properties of 21 SC Galaxies with a Large Range of Luminosities and Radii from NGC 4605, R equals 4 kiloparsecs, to UGC 2885, R equals 122 kiloparsecs. All right, last quote I'm reading. In a spiral galaxy, the ratio of dark to light matter is about a factor of 10. That's probably a good number for the ratio of our ignorance to knowledge. We're out of kindergarten, but only in about third grade.
Third grade.
Vera Rubin in A Century of Galaxy Spectroscopy, the Astrophysical Journal, issue 451, pages 419 to 428, 1995. All right, there goes on a lot more quotes. Oh, there's one more that I have to say, which I thought was really cool. So people say, like, shoot for the stars, right? Vera Rubin said, don't shoot for the stars. We already know what's out there. Shoot for the space in between, because that's where the real mystery lies. which was incredibly witty, I thought. So
yeah, let's get let's get into it. Yeah,
let's get into this. But first, we got to
Shen.
introduce who's talking here. Like, this guy is Leonard Kramer.
Yeah.
Can you?
How's it going?
Pretty good. Just ate some lunch and so fed my brain. Now not brain, stomach. Now I'm gonna feed my brain by talking to you.
Yeah. Okay.
And we're gonna feed the audience as well, so to speak, with this knowledge.
Yeah.
So before we go on, this is episode 237 of I'm just gonna call it the Shen Leonard Show for now, until a better name comes up.
Yeah, we've been drifting from space, haven't we? But we're back to space now. We're back to space science.
This one's clearly space, so this is good. Oh, sorry. Go ahead.
So you wanted to talk about Vera Rubin? Is that what you wanted to talk about?
That is correct. So we're gonna.
Oh, okay. All right. She was an American astronomer and did pioneering observations that probably gave the strongest evidence for the existence of this thing that we talked about before called dark matter.
So what I found surprising was that, like, this is another area where, like, new ideas were initially dismissed, right? I don't think dark matter was accepted initially.
Well, I mean, there was a guy named Fritz Zwicky in the 1930s. I think he lived till about 19.
We talked about Zwicky a bunch of times.
Yeah, Zwicky, and he, his observations were controversial. But the thing is, well, you can say, well, there's a whole lot more matter there than we can account for by the the virial equation, the constraints on how fast things are going as compared to how much mass is there. But you could just say, well, there must be dust, or there must be dark things, or stuff that we can't observe. And so in the 1930s and 1940s, that was sort of the idea, because you go, well, there's more mass there. Okay, so you just shrug your shoulders and say that's fine. There's other things besides luminous matter that can be postulated to explain that. And so I don't think we should be too hard on the community for coming to the conclusion that there's something called dark matter. But we can talk about it. Vera Rubin really, she kind of broke the ice on it, or however you want to say that. The influential work came in the 60s and 70s when she studied how the stars orbit around spiral galaxies. I guess. Do
you want to take a step back, and are we diving right into this, or how?
Well, I can go anywhere, any direction you want. It's not like I'm just speaking extemporaneously. And that's nice that you've got a chart. You've got a chart there. You did a good job on that. So, okay. If you imagine you're standing on a carousel, right, and it's just rotating around, or the other model is like a phonograph record. The planets, in a solar system, the planets orbit. They don't orbit like a solid rotation. Like a phonograph record is a solid rotation, where the objects further out move faster than the objects toward the middle, right? But in a galaxy. Let's see. In a galaxy, I don't know which one I want to use here.
Any one of these, or you can use any galaxy, right? So, yeah. So
in a galaxy, the thought originally was that the stars were gravitationally bound, and that their velocities would travel. Well, for example, in the solar system, the Mercury goes around the sun in 88 days. Neptune takes 165 years to complete an orbit. And so for centuries, the astronomers just assumed that the galaxies work that way. But it turns out they're wrong. And so I guess we'll tell that story about how one astronomer or a group of astronomers convinced the scientific community that the galaxies contain far more matter than we can see. And I think we can attribute that primarily to Vera Rubin. And see, when I was in graduate school, I'm sure she came to speak.
I'm gonna put you front and center. Or rather, let's do it this way. Okay, go on.
Okay, you can put me wherever you want. But I remember her. I do remember her coming to speak. I remember the content of the lecture was about these galaxies and the flat rotation. I can do a little bit of her biography. Her name. She was born Vera Florence Cooper. She was a Cooper, and she came from Philadelphia. She was born in 1928. And her family moved to Washington, D.C., and that's where, and as you mentioned, she spent countless evenings looking at the night sky from her bedroom window. And so she was like really probably a real brat about the stars and the sun, the stars and that kind of thing, but not in a bad way.
Yeah, I mean, that kind of nature starts young, right? Like you don't hear about like people in their adulthood suddenly starting to look at the stars.
Right.
For little kids that they start.
I read that she was plotting the paths of meteors and trying to understand how meteors would transit the atmosphere. She and her father built a homemade telescope, which is a hobby that people had like in the 30s, 40s, 50s. even up into the 60s, all the way up until the time when people started scrolling, or, well, really when television came on, and maybe they stopped building telescopes. But nobody builds homemade telescopes anymore. I mean,
yeah, I mean, it's not as common.
You don't have to, because you can just scroll, right? That's what I see people doing all the time, which is evidently much more engaging than
than looking up at the stars. I mean,
looking up the stars, or getting your hand on a glass blank and grinding it and measuring it and then putting it in a tube, that kind of stuff. But this was a good activity, so you can see she had an intact family and an attentive parent who tutored her, mentored her through these kind of things. So, but unlike many scientists who discover astronomy in college, Rubin, I'm sure that she knew from childhood that that's what she wanted to do. And I guess we have to say, it's not an easy career. Like in the 1940s, when she sort of, turned into a young adult, very few, a lot of universities wouldn't admit women into astronomy programs. She went to Vassar, and she studied. What did she study? She studied astronomy at Vassar as undergrad, and she had heroes like Maria Mitchell, who was a professional astronomer, and she taught. That was kind of one of her teachers or professors at Vassar. And then after graduate, well, then how people they like you meet people, and then you get attracted, and then you court and you get married. So she married a guy named Robert Rubin.
That's how relationships work, right? Go on.
Yeah. Well, and she eventually had 4 children, and something about her children. Every one of them earned a PhD in a STEM field, science or mathematics.
That's pretty rare. Like, you don't expect your kids to follow in your footsteps. Like, I mean, parents do.
My kids, I just wanted them to be whatever. I let them decide what they wanted to do. Yeah. My daughter, when she was 11, wanted to be Lady Gaga, and I said, "Great, I can retire early," But
there you go.
But we had a backup plan for her. So in graduate school, she applied to Princeton, and she had good grades, but they didn't admit her. They just don't admit women into the astronomy program.
Yeah, that was very unfortunate back then.
And Princeton had that policy all the way up until 1975, which is it's really kind of outrageous, but.
That 1975, they wouldn't admit, until 1975 they wouldn't admit women into the astronomy program.
I could be wrong about that, but that's what I read.
Right.
But there's Cornell University. Okay, so the hell with Princeton. Cornell took her in, and she was there when she had a lot of outstanding physicists as teachers and lecturers there, including Richard Feynman. But she then transferred to Georgetown University, and she completed her PhD there. Mm-hmm. By the 1960s, astronomers understood gravity extremely well, but they had there's a practical problem of how do you weigh an object that's 100,000 light years across, and so. The idea is that you can kind of look at the luminosity of a galaxy, and then from Newton's laws, you can calculate how rapidly every star ought to orbit the galactic center. And the farther away the star is, you would expect the slower it would move. Exactly like the planets around the sun. And everybody expected the observations to agree. So let's see. I think I have.
Let's see here.
Go ahead and show the slide. So
slide deck time. Orbital speed in the Milky Way.
She connected up with a colleague named Kent Ford, and actually here's Kent, Kent Ford, and he developed this technique for very carefully measuring the motion of stars in the Milky Way. And also spiral galaxies. And so here's some salient facts about him. And then our orbital speed what's expected would be that a star would orbit and then it would fall off. The speed would fall off over.
Are you showing the one that says Keplerian? That's what you're saying.
Keplerian just means gravitationally bound. It doesn't necessarily mean it's a Kepler orbit, because you have variable amount of mass that you're being attracted to. The center, it's not really a central body, but that's the idea. But what was actually observed is that the velocity curves would flatten out. In other words, it would follow the Kepler curve for a while, and then it would flatten out very far, almost like we're rotating. Not on flat rotation, not on solid rotation, but seems to be influenced by a lot more matter than is apparently there. Meaning apparently, from what you can see. So Rubin started working with Kent Ford, and he developed these really extraordinarily sensitive spectrographs, and they measured the stellar velocities with very high precision. I want to make it clear they weren't watching the stars orbit around, because that would take hundreds of millions of years. But they could measure the velocity, tiny Doppler shift of the light. And night after night, they observed the spiral galaxies, and they looked at the Andromeda galaxy, and they lined up this is the actual measurements. And so what was expected is along this blue curve, and what they actually observed, and you can see actual observations with error bars observed out to very high distances. You can see they kind of like measured along a section of the Andromeda galaxy. So the stars near the edge are moving almost as fast as the stars that are quite closer to the center, and that's highly unintuitive. It's not what you expect to see.
Right. So this is not something that anybody expected, right?
That's not what anyone expected. And I remember when this was presented it was presented to me sometime in the 90s. I don't really remember when I first became aware of this. But this is when people started talking about this unobserved mass component. And there's other things. Actually, we did a show on dark matter, I thought.
We definitely did, yeah.
Or it may have been in another lifetime, or another thread to the multiverse.
No, we did a show on dark matter.
Okay, all right. Yeah, so I think we talked about this flat rotation curve. But anyway, that's the idea. This is the thing that flummoxed everybody. They're moving the stars out near the edge, meaning out here, are moving almost as fast as stars near the middle. And I think they originally thought there was something wrong with the measurements, or maybe there was something peculiar about their line of sight to Andromeda. So they started looking at a lot more galaxies, and they saw this same result everywhere, right? And so this is the flat rotation curve that we talk about. That was talking about. So and so the rotation curve remains almost flat, and it suggests actually the numbers that they were coming up with. It suggests that there's about anywhere from 5 to 5 or around 5 times more matter than we can see, and it's not. And they've excluded dim stars or dust, or there's reasons to think that it's not black holes or other kinds of objects like that. So this is what we call dark matter. Now, Rubin was able to show this very definitively using this method. It's really Rubin and Ford. Ford was the experimentalist, and she did the theoretical work on it. The idea was not really. It wasn't her invention, because in the 1930s, and I think we talked about Fred Zwicky.
We did. That was That was on that same episode, I think. In the
Yeah, I have a slide on Fred's wiki.
you have a, yeah,
Yeah.
he's an interesting character.
And so, yeah, I didn't say anything here about it, but he was known for being kind of irritable kind of guy. He would insult people. People didn't like it, but he ended up at Caltech. He came from.
Imagine that. You insult people and still end up at Caltech. I mean,
yeah. Yeah, I forgot exactly where he was. I think he's from Switzerland. I'm pretty sure he was from Switzerland. And there's a picture of him up in the upper corner there. Right. probably pointing his finger at somebody and telling them what a fool they are. I just made that up, but I mean, but it is. But anyway, what he did was he said, look, he looked at certain kinds of clusters like nebula type of objects, and he counted up the luminosity and they were able to estimate approximately how much mass is present, and from that you can turn these spread out over a certain volume, and they say, well, this has a certain amount of potential energy, and then he can look at the Doppler shifts, the spread of the Doppler frequencies, just like Ford did. And he said, look, there's way more potential energy in this than we expect from kinetic energy. And he published that and called, I think he called it missing mass.
Okay, so he used the virial theorem.
The virial theorem, and that's a term that comes up in physics and also chemistry. A lot of times there are virial theorems for certain gas laws. Yeah, but
it's just showing virial theorem is what, just showing the total energy.
That right? The idea is that in order for the object to remain bound, in other words, if there was no gravity and everything was flying around, it would just fly off to infinity. Okay, but it has to be bound, so everything's in orbit. It's not kind of closed orbit, or it's confined to a certain volume. And so in order to do that, the kinetic energy of the objects has to be less than a certain fraction of the total amount of potential energy there. There needs to be more potential than kinetic energy. Otherwise, everything flies away. So that's very intuitive, right? But what he found was that there was a huge amount of kinetic energy, but the amount of potential that he could determine from the visual appearance, the number of stars there was a factor of 5 smaller. So it's the same principle that Professor Dr. Rubin was observing. So it's the same idea, except that she saw that in the rotational velocity of the
rotational curves, and Zwicky saw it in what?
Well, he treated the whole volume as like a gas, like. So he just looked at the random velocities, the spread of random velocities in the object. So he didn't have any structured velocities. What Vera Rubin did was that they were actually able to show the velocity as a function of location along the galactic disk. So with Zwicky, who came out with his observations, I think in the late 30s, most people, and he said there's missing mass. And it was a good paper. I mean, there's nothing wrong with those papers. It's just that people just kind of like shrug their shoulders and said.
33. Yeah, Fritz Zwicky applied the virial theorem to estimate the mass of Coma cluster. So that's a large cluster of galaxies. That's over 1,000.
Yeah.
And then discovered a discrepancy of mass of about 450. Which he explained as due to dark matter. So I guess when he stated that and published this paper, nobody really said anything.
Well, I mean, the idea that there's some kind of invisible matter is extraordinary, right? Now there are things that you can attribute it. You can postulate or assume, make the assumption. Well, there's a lot of things there that are dark. Okay, so there's mass there. It's just not luminous mass. right? And so that's how that was kind of like set aside because of that. But it turns out that his observations are very relevant and very supportive of Rubin's theory that's become really, and so this all developed like during the 50s and 60s. By the late 70s, this discrepancy was impossible to ignore, and so that's what's going on. So there's this thing called dark matter, which we've talked about before, and so what is it? What is dark matter? And so oddly enough, we don't have an idea. We don't have a good idea, and we've done shows on this.
We have we're basically said, hey, like we still don't really.
Yeah. So I will defer again to Turek. What's his first name? Neil? No.
Neil Turek. We did an episode on Neil Turek.
What's his Neil? Yeah, Neil Turek. Okay,
yeah.
I
196, guys. For anybody who wants to watch it. Keep
going. So Turek's idea is that, and he goes through all of the. It's very compelling to me. He thinks that it's a kind of what's something called sterile neutrino. So there's a symmetric kind of neutrino that doesn't interact with the weak force. Ordinary neutrinos that we know about, they only interact through the weak force, and the weak force only participates through left.
This is his theory, Neil Turek's theory on what dark matter is.
Yeah, right? That's right. Now I don't really know if it's Neil Turek's theory, but he's the one that's best articulated it to me in a way that I think I understand. And so the dark matter is a particle. It's a kind of neutrino that's much, much heavier than the regular neutrinos that we know about. And it doesn't participate in any of the forces that we that we're aware of. Neutrinos themselves are so weakly interacting; they only participate through the left hand polarization of the weak force, which is on. So the idea is that nature produced an alternative of that would participate through right-handed polarization, and he also makes Turek also makes some observable, falsifiable assertions about it that are being worked on now. But dark matter
let's bring it back to Vera Rubin here.
Yeah. Well, I think it's important to talk about the dark matter a little bit.
Right, of course. Mm-hmm. Yeah. But from Vera Rubin, what she was observing was these that yellow line you're indicating, right? That the rotation stayed
right. And there's nothing controversial about these measurements. I think that they're very, very well established for many spiral galaxies.
At that point, like in the 1930s, when Fritz Zwicky was doing his work, so was Rubin automatically drawn to that in the sense of like, hey, this must be what it is. Like there's dark matter that we can't observe.
That's kind of a good question. I don't know. I don't know what she expected to see. I think that they were trying to. It was just a general characterization of the velocity and the total versus the total amount of matter there. I don't know what was motivating her other than her own curiosity.
Right.
So this rotation curve, wherever it is, this rotation curve is really quite an achievement, and it speaks for itself.
Like determining this I mean, I don't know enough about astronomy to know how you would do that. I guess you have to observe, say in this case, Andromeda Galaxy for like, how would like you have to?
No, they were using the spectrograph, so they would look at a particular point here, right? And they would find out how fast the matter there was going, and then they would project that onto the plane of the galaxy, and then they would move to the next point, right? And then they go to the next point, and so forth. And then they would go through, and then this is the average. This is sort of the averaged rotation curve from a center point of the galaxy.
Yeah, right? Yeah, no doubt. Okay, I see. So
yeah.
if all of matter is just this visible matter that we see, then we should not be seeing this orbital speed. Furthermore, right. I've read that there wouldn't, if it was going at this speed and we didn't have more mass, it would not, it wouldn't stick together. There wouldn't be a galaxy.
It wouldn't be a galaxy. The galaxies are held together by this extra mass, or they would slow down. In other words, we wouldn't have this. There'd
be two alternatives: either the galaxy flies apart, or your orbital speed as it goes further from the center should decrease.
That's right. So this difference right here is really quite a challenge, and that's where the gravitational, the dark matter.
Do you know where she was doing this observation? Or
I don't know.
Just curious.
I think they. I don't know. I don't know that. I don't think that they were using any extraordinary.
Right. It was just some ground telescopes. Obviously, you have to do this for a multitude of you can't. There must be a lot of data, right? You can't just say
there's a lot of data and many galaxies. Just one galaxy right after another, and they saw the same thing over and over and over again.
Right. So that's pretty crazy. You go to every single one. And
yeah. Let me see. Oh, here's a picture of her looking through the telescope. These are glamour shots. Okay. These are astronomical.
Not that particular telescope, but Kit Peak Observatory. Yeah, it's a great place. Glamour shots, right? This is not how.
Just joking.
Well, nowadays, Leonard, as you probably know, so when I did astronomy research for a little bit one summer during college, the professor I had then was telling me how we don't do any research by actually looking at the telescopes. It's just point and click on the computer and then download the data. So,
well, that's looking. That's just
looking with the camera. Yeah, there's no more looking at through the eyepiece like what you're showing here, what she was doing in the 1960s. So
yeah, I don't know. I literally I think that these probably are just photos either for the university or just for her resume. I don't know. I don't really know where these pictures came from. I do notice I like her fashion because I like paisley.
Yeah, absolutely. It's a good right there.
There's some black and white.
It looks like galaxies in the background on that chalkboard.
It does look like there's some.
That was the first one you were showing, the Andromeda Galaxy. That's showing the anyways. Okay.
She got many honors, numerous awards, and National Medal of Science, Gold Medal of the Royal Astronomical Society. She never got the Nobel Prize.
Right. There's some controversy about why she didn't, I guess.
Well, astronomy is a challenge for the Nobel Prize because there's some criteria that you have to meet that generally, just looking at something up in the sky, it has to have some relevance. I don't really know what the rules are. But a lot of us think that that this work was worthy of a Nobel Prize.
Yeah, absolutely.
She died about 10 years ago. And before any of that, before she could get further considered for a Nobel Prize, and her legacy is probably
I'm gonna say one other thing that she did that was notable, is the fact that she discovered not everything in galaxy needs to rotate the same direction.
That's what she discovered. Yes, that's right.
That some gases and stars can move in the opposite direction of the rest of the galaxy.
Yes, I think that's true also. Yes.
Yeah. The counter rotation.
Counter rotation, and it's kind of obvious. I mean, that you would see some stuff like that, but I think the physics for things counter rotating is pretty strange. That's
Right.
a peculiar thing. I would say, you know, she has an observatory in Chile that has just recently come online. I think I have a slide. The Vera C. Rubin Observatory. I would say this is an honor to her, and its mission is to map the southern sky, night sky, every night. And there's it's like a long campaign to observe the southern night sky night after night for 10 years. And they expect to be able to see like variability, the asteroids, exploding stars, distant galaxies, and phenomenon that we haven't imagined yet. And I would say there's kind of like, can I say there's sort of poetry in that, you know, that she has a observatory which has only just now come online within the past 2 years. That, you know, this she revealed an invisible universe, and now she has a dedicated a monument to her that is dedicated to discovering what we have not yet seen. So
Yeah.
I think I might have a picture. This is one of the initial images that came from the Rubin Observatory, and it's in Chile in the Atacama Desert.
That's incredible, that picture.
Yeah, it is incredible. I think most of what you're seeing there are galaxies, and
wow.
So this is called First Light. The universe comes into focus. First image from the Rubin Observatory. I was going to say it's in the Atacama Desert in northern Chile, and that's a high altitude, very low humidity.
Right.
And there's good seeing, you know, virtually every night of the year. It hardly rains.
You can, I mean, getting there will be a challenge, I guess, unless you're an astronomer.
And I don't even know that you need to get there exactly. I think it's all electronically.
Oh, really? Oh,
yeah.
It's like controlled remotely. Like you could be in the world. Yeah. Okay.
Yeah.
Makes sense.
So
time on the telescope. I think that's how people do it these days.
That's pretty much all I wanted to say about it. It's gonna be a short show, but I mean, I would say, you know, science advances not because someone invents a new theory, but because someone refuses to ignore inconvenient observations, and that's what this is. Vera Rubin looked through a telescope expecting an answer, but the universe gave her another, and she trusted the evidence, as we should. And by doing so,
more than the prevailing theory. If the prevailing theory does not match evidence, you should trust the evidence.
Yeah. So some people have trouble with that sometimes. I've worked in places like that.
Yeah, like, well, that's where you reject truth, right? Where you basically then science will never advance if all you ever do is only accept evidence that already matches what you believe.
I could. Let's not go there.
We're not going to go there. and we have talked about like how like certain scientific theories are like you can't even falsify it, so you know
they're unfalsifiable.
And
like that big fight we had over what are the needles that you put in the acupuncture? Remember?
Oh my God! I just got that. Well, I do that every 2 weeks. So
the acupuncture, which I think is pseudoscience, and
we're not going to go there, Leonard. I don't think science. I just think modern scientific theory maybe takes some time to catch up at times. But
okay.
So
anyway, she changed our picture of the cosmos forever. and it's pretty cool. It's cool stuff. It's a big challenge. It's probably a particle in my mind. I mean, the dark matter is probably some particle that's not in the standard model, and it's probably one of these sterile neutrinos. But that's maybe for another day. She also has one other tribute was that the company that makes the NVIDIA.
Oh yeah. They recently came out with a Vera Rubin line of.
They have a tradition. They've established a tradition of naming their top of the line chips, most advanced chips, after famous scientists, and so they had a Blackwell. And some, but anyway, their latest is the Rubin chip, and I don't know what they're working on now, but that's something that's in her legacy.
This year,
and that's kind of all I wanted to say. Let's see if I have any other slides.
It's a next generation AI supercomputing platform.
Yeah, here's the Doppler shift. I mean, this is how we measure the velocity. And
so the Doppler shift is how we know, like, away where, right? So hey, can you go back to that?
So
go back
to
the
Doppler shift. You want me to explain Doppler shift, or maybe you can explain it? So if a light source is moving toward you, the frequency of the light appears to be shift to a higher frequency, which looks more blue. Okay, blue light has a shorter frequency than red light, and so we say that if it's moving toward you, then it's blue shifted, and so you'll see that that all of the spectra will be shifted a little bit toward the blue. And if it's receding from you, if it has a component of velocity receding, moving away from you, then it will be slightly red shifted, and that's the whole physics that gives you the velocities that are that we're talking about. So that's basically how and it's, you observe it with sound waves too. And I guess I'm obliged to mention that, like, when you're sitting in traffic and a railroad train and a train is driving by right in front of you, when it's approaching you, it sounds like it's higher in pitch, and as it gets closer and closer,
the pitch goes down. And ambulances and cop cars as well.
Yeah, so that's the Doppler shift, but for acoustic, for sound waves.
Yeah,
the same thing applies to light.
Okay, yeah. So when we observe that, that's how we know, like, hey, what things in the universe and the galaxies are, how are they moving relative to what we see, right? So yeah.
So that's all I wanted. That's all I know about her. I don't know anything else about her. I think what?
So, I said we don't have to talk about this for a whole hour. Sometimes 45 minutes is enough, and I think we covered the major parts. So I will say thanks everybody for watching. Appreciate you guys who continuously offer your viewership and support. And support can come in many ways, whether you want to just like, subscribe, and share this, that'd be great. Or you can also go to patreon.com/sg2space, where you can follow along whether you want to donate or not. That's fine as well. And with that, feel free to leave any more comments. If you're also doing this, what do you call this? If you watch this at a non-live version, that's fine as well. We will check back later and definitely respond accordingly. And so,
I wish people would comment or say something. Most people are afraid, or they're too busy.
There are people that like this. I don't know who this tapeworm 3673 is, but
tapeworm.
Do you see the side column? Do you not see it on your interface? Maybe not. So I answered the question though. I'm putting on there. Hey,
I see.
Yeah. So, like, seeing as how the show is coming to a close, I have a question. What if instead of the universe expanding, what if everything's getting smaller? Like an atom losing energy, shedding into light is just shrinking of the illusion of expansion, but it's truly shrinking. And I said, hey, look, we just covered the Doppler shift. That's how we know that the universe at large is expanding. So because most things are receding from us.
Maybe we need to do a show on that, or maybe we need to do that show again.
I think we could talk about that. Like cosmology is always a recurring topic that we can go back to. So
And
yeah,
and it happens to be something that I'm pretty interested in. So
I know. You're yeah. Let's okay.
yeah.
We can talk. I mean, we talked about cosmic inflation in episode 218, but that was a year ago. So we could
Yeah.
talk about the universe at large.
Awesome.
Let's do that
All
next
right.
time.
All
All
right.
right. Take care, everybody.
Yep. Shalom. Mwah.
Shalom. Oh yeah, and then what was that? Okay.